basically just start a stack project and get going. Oh, I gotta put something in the Discord. Hang on 2 seconds. Yeah. Okay. How is everyone today? Need to use 1330. And this is lifting your function. Okay. Do 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 do. What's going on, Count Oren? You tuned in on time today. I think you were late on Sunday. What's today? Tuesday? Yeah, I think it was Sunday. How are things? Git. That's not what I want to write. Let's build this quick. Make sure we're good to go. See, there's a few people here. How's it going? I'm Barry. I write Haskell code. If you've never seen this before, we're gonna learn about Haskell. So hope you enjoy it. Here we go. The first thing we're gonna talk about is just a reminder for folks who have never been here before. What is a functor, I suppose? So let's start there. Ugh. All right. So, essentially this is a functor. So basically the idea with a functor, if you've never done this before, or have never been to this channel before, where were your messages, Oren? Were they in Discord or Twitch? I'll have to check my... Okay. I don't check Twitch very often, so I must have just went over them. So yeah, I can look at them. So probably easier to reach me on Discord if you would rather. Okay, so anyway, we have this F, and this F can just be some sort of structure with some A's inside of it. Okay, so it could be like a list, it could be an optional type, could be really any container that you can put a value in. Okay, and then we have a function which takes an A and converts to B, and then we put that back into the box. Oh, okay. I can go. Let's see if I can find them. How do I look at here? I don't see any whispers in here. Count Oren. Okay, here we go. Okay, so I'm gonna read this, a little bit of this anyway. Talking about state. So yeah, last time we went really deep into state, trying to make sure we understood what it was. Let me put that code up on the screen real quick since we're talking about this. Okay. Let me put this over here so that I can read chat as well. Okay. So see the state monad as a function. The box of this monad is a function that takes a state and returns a tuple of value to be returned state, and that is all. Fmap in this monad context will create another function out of the first one that will take another state and return another tuple, applying the map function over the right side of the tuple. While bind, aka this function, probably have it written here. This function bind will return a new function, which in the implementation of it will work. Apply the bind function on the right side of the tuple and returns another state. Get returns a state and puts the state in both the return value of the tuple and the start part. You can see it as a function that takes a state and return a tuple of state and state. Yeah, I think I understand that part now. Put with a new state argument will create return a function that takes an old state and return a tuple of unit with a new state, which will ignore the state that's passed to it. Yeah. I think we figured out most of that after playing with this for a while, but it did take quite a bit of time for me to feel confident about this. It's pretty tricky once you first start. I think once we get into like reader and stuff, it's gonna be even more tricky. So hopefully we get there. Okay, so let me go back to where we were. So map or functor map basically just takes a function that converts A's to B and a container of A's and converts those to a container of B's. So there's like a really simple example of that we can quickly show in the REPL. So you can write like fmap +1 on a list of a few numbers. Oh, well, right. Where's my... because I wrote that in that lib, because I wrote that in lib, I can't do that here. So I have to write prelude dot to differentiate between lib dot and prelude dot. We're going to delete that here in a second, so this will go away. But anyway, the point is that you're taking an A, and in this case, you're really making another A by just adding 1 to it. But you can also convert these to a different type if you so choose. So that's an fmap, and in this case, the container is just a list. So, and a list represents a non-deterministic calculation, more or less. Do what on state? Well, we're gonna come back to state. So, what we were doing before was getting ahead of ourselves. So, I mean, I guess we can do that, but I'm trying to think of what we would fmap. So we could fmap a +1 on this, I suppose. Ugh. What? What? Didn't I call it real world? Or did it counter? What the heck did I call it? Inker counter real world. So we could do something like, I think. Uh, I'm not warmed up, so you've asked me to do something that I think I need state T is really the problem here. So I can't do this. I need to do, yeah. And then we need to, because the inker counter real world doesn't have an input, so I need something to actually operate on. I can't operate on void. Unit. I keep saying void. I mean unit. So now we can use this somehow. Right. But I need to import, what is it? Control monad trans state. And then we can run eval real world and 0, and it should print back 2. Oh, I was just trying to do it with something we already had. But yes, in theory, you could do something like that, I guess. Mm-hmm. So, okay, so you're saying something like, get? Oh. So this is kind of like, what is this? This is just essentially +1, right? Then we would run like eval state t +1 0. Okay. Yeah, sorry, I was thinking out loud. I understand what you're trying to ask now. Or not ask, but show me. Okay, and then what's the type of +1? Is it int identity int? Oh, it actually, okay, so it's even more generic than that. You just need to give it a B and it will choose what you need. I suppose we can just do, oh, okay. It doesn't, oh, I mean, you're getting back, I see. You're getting back a monad of A. In this case, it's probably just printing out 1 because you're in the IO monad or something. In this case, we're in the IO monad. Okay, that's cool. Okay, back to where we were. So we talked a little bit about functor. It says the power of functor is rather limited, though. The set of functions that can be lifted using Fmap is restricted to those that take exactly one argument. Alas, many interesting functions take several arguments. Some primary examples are arithmetic, right? Like any binary operator. But you can write lifted versions of those things. So just as an example, what just happened? That was weird. So we could write like this function. Let's do num a monad m. M a. Okay. M a m a plus equals 2. So we're gonna write this in kind of probably funny looking notation first. Maybe not funny, but it's really a weird way to write it. We'll just write my. M x. Okay, so this is basically a lifted plus function for any situation where you're working with two monads. So as an example, you could have like, I don't know, oops. Maybe int and then you could write like excuse me, something like this. Okay, so very simple looking function, but now this generalizes over any monadic container and any numeric a. So you could add any of these together as long as that was your shape. So anyway, that's like a generic lifted plus. Yeah, so in essence, all we're doing is unwrapping the monadic boxes with the left arrow operator and applying a pure computation, right? Our pure computation is just a plus b at this point. And this is sort of the idea of lift a2, so you can generalize this further, and I'll write it under here so we can see it on top of each other, but you can see lift, well, we don't want to call it lift a2 because we're going to get to that here in a second. So now you can have a num a monad m, and an a. Oh, actually, yeah, no, a, right? Oh, I guess technically it doesn't need to be an a. I see, and it also doesn't need to be num. MC, right? So lift 2 is I hate that. I need to figure out how to make that not happen, but I don't know how. Oh. Use. Oh, okay, so I should mention that this HLint suggestion right here is actually going to just say use applicative. So it's going to, we're going to, well, let's just show it. So you can apply this HLint and it will just take F and apply it to this A, and then Fmap that onto the monad of B. So it's just to like shorten things up, and you know, it's just a easier way to write this. Right? That's just HLint, so it's just making that suggestion. So we can do. I keep pressing the wrong button. We can do this. It means exactly the same thing, but we're gonna go even one step further. So just bear with me, and we'll deal with that. Okay, so the point I think that's trying to be made here is that there are basically lift n functions where n is some arbitrarily high value defined in Haskell's standard library. But if it's not, you have to define it yourself. And then you can write the generic one basically, but you know, you just have to fill in all the details. You can't do it easily. Okay, so hang on. Yeah, so it says either your base library provides enough variations for any reasonable number of arguments, or the functions are generated by some kind of macro. Either way, you're going to end up with a lot of duplication. The good news is that we only need one function on top of fmap to lift any function with any number of arguments. Consider a function g with 2 arguments, like this. Let's just leave that alone for now. So we're going to consider a function a to b to c. Also, hello viewers. How's everyone today? I haven't heard any peeps, so feel free to say hi. By lifting it through fmap, we are able to apply it first to an argument of a monadic type. The result, however, is a function wrapped in a functorial or monadic context, so we can apply it to further arguments. So let's write this. So if we write, I'm gonna write this here, fmap g onto on a monad of A, right? You're essentially going to have a type that looks like this. We'll use M to denote that. M of B to C, right? And then that is something that you can apply somewhere else. So then you can use this function to apply it to your MB. So, but you need to get that function out. Right. So you really want something like this, basically. MBC, MB, and put this whole thing in parentheses. Well, we don't have to, we'll just use an arrow to separate them. Right? That's what we're looking for. Because the way this works is you're basically partially applying A. So all you need is a B to get you C. All right. So now we're going to write the definition of this function, essentially. So We're going to call it app for apply. So if you have any questions, also feel free to spit them out. I can do my best to try and answer them. We had a lot of interesting questions last time from folks who aren't super familiar with FP in general, so that was kind of fun. Well, if it's a monad, we're gonna do this in a slightly different way next time, but we can do it this way for now. I assume this is what, what answer they're looking for. B. Because we can just do everything in do syntax. B. And this is the same HLint thing. This isn't an error. So it's just suggesting to use the applicative style, which we technically wouldn't know if we were doing this book. So anyway. Okay, so it says, now we come to one of the moments in which all the small elements in functional programming fit together in an almost magical way. We need nothing more than Fmap and App to be able to lift any pure function regardless of the number of arguments. Take a function that has 3 arguments, f, a, b, c, d, f2, a, with 3 arguments that we want to apply in a monadic context. That is, we want to be able to apply it to values x, y, and z. Right? You can essentially now just write fmap f x app y app z. Okay. I can prove it to you. We can just write it real quick. So this would be lift 3, but we'll write it. Well, I mean, it's fine. We need D. I just want to make sure it type checks because that's what we do. B, M, C, M, D. Lift 3. F, X, Y, Z equals fmap f x app y app z. Okay, so that's what lift 3 looks like using fmap and apply. Oh, I forgot to put something in here. I just want to note that this was an exercise. 3.1. App. In specific instances, when we implement applicative later, this becomes a lot easier to write. But because we have to be generic in M, you know, that's the reason we have to write this way. I think that we would need the do here, otherwise we can't unwrap the monadic context from the function. So when we get to the actual and applicative cases, you can unwrap these very easily with pattern matching, and then it's very easy to extract this function from the monadic context. There might be another way to do it that I just am blanking on right now. We'll see. Okay, so in summary, we have found a small set of primitive operations that we can use to embed pure computations into the monadic world without too much pain. I would agree with that. So up to this point, we have seen app as a byproduct of lifting a pure function into a monadic context. But actually, this abstraction has a life of its own, independent, completely independent of monads. Applicative functors, or simply applicatives, applicative functors are those context containers or boxes for which you can not only lift unary functions, which you get from functor, but functions with any number of arguments, for which you use app. Note that in both Haskell and Scala, the abstraction is defined as extending functor, from which we inherit the mapping operation, right? So it's going to look like this. I'm pretty sure I can write it from memory, but we'll see. So it should be pure. What's going on, Edwin's Roar? I like the first time I realized that was like a person waving. I really enjoyed that. I think that's pretty funny. And F A B F A F B, I believe. Oh, E, yes. No, star. Okay, and then we're just going to comment that out because it's already defined for us. And we don't want to have to deal with that later. Okay, so that's basically what this looks like. So you have two functions. Yeah, I like it. I think it's kind of cute, actually. So an applicative comes with two functions: pure, which is basically taking any pure context or any pure value and embedding it into an applicative functor context, and apply, which is exactly this app that we implemented before. But you'll note that we don't use a monad constraint. We only have a functor constraint. So yes. Yeah, well, no, we're not implementing flat mapping. We're implementing the applicative, which is, I don't think is, flat map is bind. So this one, check it out. Emotes. Bam. That's flat map in Haskell. I think we've already done that, if I remember correctly. Keeping all of this straight is now kind of hard because we're doing multiple books at once. I forget what we've done and what we haven't done. I mean, we've definitely implemented bind in HPFFP, but I don't even know if I did that on stream, so it's hard to keep this all straight sometimes. Okay. Okay, so it says, this is another exercise. So, by the way, that's, now that I'm thinking about it, we have, Yeah, I mean, so this is a natural extension, has a natural extension to flat map. So but it's not quite flat map. I'm not clicking in the right spot. Hang on. So we have so this takes MA A2 sorry A2 MB and makes MB. So that should look familiar to you. That's the flat map. Yeah, so I want to show this real quick. So I think we have, oh, I spelled it wrong. We have apply, bind, and I think it's just map. What's the third one? Fmap. I'll get there. I don't use them very much. I should use them. Here we go. Those are our emotes right now. We don't really get a lot of them, so. Mostly because I don't know how to use them in chat. I usually just talk, so other people would have to use them. Yeah, but that's flat map. So when you're thinking about flat map, just remember that list is a monad, and that's why you can use flat map. I assume that's probably why you're using it anyway. Okay, so exercise 3.2. Implement Fmap in terms of pure and apply. We'll call it Fmap prime as to not conflict. So can't type. Do I have to put this in parentheses? Oh, because I'm using the wrong function. Oh, I get it. Okay, so it's saying use fmap because so our linter is cheating, right? Our linter knows that this is fmap because this is a simple fmap operation. So it's saying just use fmap. What are you doing? But we don't want to. We're trying to implement fmap in terms of pure and apply. So that's how you would do it. sometimes having the linter on is a good thing and a bad thing. So when we're doing stuff like this, the linter is a bad thing because, you know, it understands that this is just Fmap and it understands that this can be simplified. But that's not what we're trying to do. I'm trying to write the code that it expects. Or maybe the code that would make sense at this particular time. Hopefully that makes sense. Oh, also, before I forget, someone followed on Twitch and I missed it before, and it's HMay Twitch. So if you're hanging out, I really appreciate the follow. Okay. I feel like I missed reading something. Hang on. So yeah, in GHC 8, I'm not sure exactly. Oh, you're here. Hey. So what I like to ask people, yeah, what was it, yesterday? It says 2 days ago. Maybe it's just wrong. But hi. Do you are you a Haskeller? Do you just like functional programming? Tell me about what you like. Yeah, I can keep you honest because I can see when. I have the power of the internet. Okay, so one fair question is, are there applicatives that are not monads? That's the question the book brings up. You're learning Haskell yourself, HPFFP. That is a beast of a book. I commend anyone who finishes it. We finished it a little while ago, I would say. Probably, I'm not even sure, 2-3 months ago. I wasn't allowed to put any of the videos on YouTube, so unfortunately they're lost in the ether. But we're kind of moving back into some less technical stuff, so that we can solidify our knowledge as well. What chapter are you on? It's a beast of a book. The reason I started streaming was to keep myself honest to finishing the book. Chapter 11. Okay, so you're I forget hang on, I have the book here. I don't think you'll see anything. Making sure. Okay, I'm trying to remember what chapter it is. Oh, algebraic data types. Wonderful. Yeah, this is a good chapter. Good chapter. I don't remember exactly what chapter we started on when we did the streaming, but it's a great book. It's a really good way to learn. Okay, so there apparently the classic example of things that are applicatives and not monads are the zip list functor. A zip list is merely a list, but zip lists behaves differently when they are combined applicatively. Instead of obtaining all combination of values in each list, the effect of this functor is to zip each value in the first list together with its corresponding value in the same position in the second list. So let me show you an example of that if that me reading out loud is not helpful, because I don't think it's particularly helpful in some cases. So if we had this function, you'll see that when you use the applicative for list, what you actually get is combinations of each of the first value with both of the values in the second list, and the same for 2. So you get 1, 3, 1, 4. The effect of this code, just so everyone's clear if you've never seen this before, is you're essentially taking 1 like this and 2 like this and applying it to 3, 4. Oh yeah, but you need a special extension to enable that syntax. But this is basically what you're doing. You're partially applying this function to each value in this list via Fmap, which hopefully that part's clear. And then you're using apply to take these functions and then apply them to each value. So you can write it this way. You can also write it just for reference. If you don't want to write it that way, you can write it like this as well. Oops. It works just the same. So this requires a language extension called tuple sections, and this is just pure Haskell code. Okay? If anyone needs a little more help with that, just let me know. If you can't read it either, let me know. All right, now there's something a little different about these zip lists, so let's do that. So zip, do I have to import something to get zip list? No, it is a low precedence operator compared to Fmap. So Fmap applies first, so this is what's evaluated first, and then the apply. I don't remember how to figure that out. Hang on. Yeah, so I don't remember exactly how this works. It's been a while. But this behaves as if you had parentheses around this. I think I don't remember what function applications precedence is, and I think this can be a value of like 1 to 9 or something. We can look it up. I don't know why I'm just not looking it up. Haskell precedence operators. Yeah, okay, so although this doesn't say anything about just function application, so this isn't particularly helpful. Haskell precedence of function application. Let's see if there's... Yeah, so this is the Haskell report is the definition of the language. Section 3. This isn't helping. Yeah, but does that actually help? Maybe. That sounds weird though. Doesn't I feel like that sounds weird. Oh, here we go. Something in here about... There it is. Function application has highest precedence. Yeah. So function application has the highest precedence. Therefore, where'd the code go? This somewhere there. Sorry, I had a hard time finding it. There's no highlighting or anything. So this happens first, and then the infix operator happens. Does that make sense? That's actually a useful thing to know. I should probably know that, but it is what it is. I also need to go figure out where I get zip list, because I don't know where that is. It's in applicative. So import control applicative, and then we should be able to write fmap, comma, zip list 1, 2, 3, 4. Yeah. Okay. And then we can, just to make this a little easier to read, we'll do this. So this just effectively applies your function on the zipped lists. Although I guess by default that's what zip is doing. Interesting. Oh, that's cool. Okay. So anyway, that's that. It says write the functor instance for zip list. It has the same behavior as for normal list, except the new type wrapping and unwrapping. Okay. Oh, not here. Here. So we're going to redefine the zip list. Uh, Functor? Functor. So just, yeah, so fmap is going to be oh, okay, okay. I was like, wait a second. Am I missing something? Because it doesn't say implement applicative. It just gives you the applicative instance. I was very confused. What was going on? Because I can't imagine that this is hard at all. It's just going to be like this. So essentially what you're doing is you're just getting the list out. So this just gives you list of A. Then you're using your normal fmap for list, and then you're just sticking it back into a zip list. And you can probably do this even easier by just doing zip list and then just write that. So you can unpack the list of A directly from the list as zip list via pattern matching. You don't need to play this game if you don't want. And I think technically these are like ultimately this would lead to the exact same code because the new type doesn't actually embed any overhead for working with lists. So it doesn't matter which way you do it. It should be exactly the same ultimately. Okay. So then it gives us the applicative instance. So I'll just write it in here. I figured it would make us implement it. I feel like we implemented it in Haskell programming from first principles. Excuse me. Oh, right. So Okay, so this is kind of interesting because apparently the implementation of pure of x, shouldn't this be pure of x generates a zip list of infinite values, which is interesting. I wasn't expecting that. And this looks pretty strange. Zip with an F and an X. Can you just zip with, what's the, that's a very strange. Can we not zip with this? Does it just not work? I'm afraid it's going to fail, but now I kind of want to try it. It would be fine if it failed. The question is it going to work with infinite lists? That's the question. So we'll have to try that. So let's see here. So we want to say, I don't know. We can do what we did before. Just do. Oh. Hang on. Zip with needs a binary function that takes values from the two applicatives. Yeah, that's what $sign does, right? Just taking no, it doesn't take a binary function. It's a unary function. It has to be. Well, I guess it doesn't have to be. Because it can be partially applied. I see what you're saying. Hang on. I see what you're saying. I think. Hmm. Hmm. Sorry. Thank you. Thank you. This should just be plus. There you go. Yeah. Thank you. Thank you. Sorry. Remember the type. The type of this is a unary function, not binary. Okay, so the only thing that I'm concerned about, I guess, is so if I use pure here, I get an infinite function. So I should be able to just write pure 3 here, and in theory I should get 4, 5. Okay, so no, it works. I think we're okay. I don't know if there's a actual difference between using the $ here or the explicit function application lambda. I don't even know what to call it, because it's literally just function application. It's literally, it was this, just for anyone who is curious. But I don't think there's any difference. So I'm gonna leave it as $ because I like that better. And then the other thing I want to do is replace this with a $, because, and this as well, because I prefer, I prefer this style. I think this looks better as well. I think that's what your smiley face is about, or your comment is about. I think this looks a little better. Actually, you know what? Hang on. Let's look at something, because now I'm interested and I'm thinking about it. Oh, right, but this is actually kind of a funny function, isn't it? Because it's actually doing some silly things. Not silly, that's not really the right way to say it. Just click here. Yeah, it's just a low precedence. Actually, what other functions have this shape? That's really the question that we're asking, right? So that's just apparently a strict version. I suppose the other thing we can do is say, look, it should only be in base, probably. Not really sure. Anyway, I think it's correct. So let's just move on. I was wondering if there was maybe like a version of that didn't have the precedence behavior that it has, but it's fine. Okay. So there's sort of a style that goes along with this type of programming where you essentially write things like this, right? And we sort of wrote it before when I did this code. Let me just show it real quick. So this is like the applicative style. So you're going to see this quite a bit. You'll basically take a function, you'll fmap it onto a container, and then you'll use the apply to apply it to something. And this is kind of the style that you'll see. And we've written a lot of code like this when you're doing like parser combinators, because you'll end up with like partially applied functions often, and then you just fmap your function to some other container, and then it's a partially applied function, and then you apply to get the rest of your arguments. So it's a pretty cool style, actually. So actually, as an example, let's just write an example here using do syntax, because I guess why not? It's in the book, so that's why I want to show it. So we'll just show it real quick. But it's essentially what we've already done. I don't like that style. It's just not my style. So you can just write like this and you get that, but you can equivalently just write plus fmapped 1 2 3 apply 4 5 6 if I could type, and you get the exact same thing. So it's kind of just a style thing. You don't have to write the do notation. And there's actually one positive thing about this that is not super obvious, is that you're actually using a less strict requirement by using this syntax. So this syntax only requires applicative, whereas this syntax requires the monad constraint. So you're using a slightly lighter constraint in the latter than the former. There's actually ways around that. Haskell has a, I think it's, hang on, we can look it up. I think it's applicative do, which we're going to talk about here in a little bit. But with applicative do, you can write this, but actually get this instead. So you're not actually using the monadic context, you're using the applicative context. I have no idea how it decides which one's which. Well, yeah, you get more power with the monad. That's correct. If you're in the monadic context, you get more power. But in this particular case, you don't need that power. So there are cases where you do need the monad, but in this case, we do not. So that's a good point, though, Oren. Anyway, it's time to drink some water. So we should all have a glass of water or a drink of water. Thank you, Mubot. Okay, there we go. On the other hand, it says not everybody feels comfortable with this style of code. Its premise rests on the assumption that programmers will ignore the symbols in between the functions and arguments and just take them as a reminder. This application is running under an applicative functor. On the other hand, these symbols are obscure for most beginners, so they stand out most in the expression, making it hard to decipher what is really going on. I'm not sure I completely agree with that. I can see how this syntax is easier to read from a beginner's standpoint, but there are definitely cases where I actually like using the applicative syntax. It actually made, for example, when we were doing the parser combinators, I think using the applicative syntax actually made the code clearer. And using the monadic code was a little more annoying. It just didn't look as nice. That's all. It actually looked better with the inapplicative. Obviously, that's completely subjective and has no theoretical bounds. But anyway. All right. So apparently, there's also there's other alternatives to this in other languages. So in Idris, can I get Idris and REPL it? Open that, sorry. Open this. REPL it? I've never seen this before, so I don't know if you can get Idris in here. Can I just open a REPL without signing up? Okay, I can't get Idris. Does anyone know where I can get like a Idris REPL real quick? I certainly don't. Anyway, in Idris, apparently you can write things like this. Whoa. It would be like plus I think. This isn't valid Haskell, but in Idris you can write something like this for applicative, I think. I don't know exactly how this looks in Idris, but let's pretend that it's like this. I don't even know how to define lists in it. Try Idris can do. Thank you. Also, hello. Try Idris. Oh, nice. Okay, cool. So can you define a list like this? It looks like you can. So in theory, we can write, can you use sections? Or do I have to write an explicit lambda? Let's just try it. Sorry, I don't really know. Also, hello, Active Fireball. How's it going? Thank you for lurking. lambda. I really don't. I don't know enough about this. Does anyone know how to define that? Is that actually the problem? I legitimately don't know. This is just in the book. I'm just trying to, like, root it. Well, anyway, apparently you can do something like this. Apparently there's actually a Haskell package which lets you do this. So let's go check that out real quick. Applicative quoters. Woohoo, we found it. All right, thanks. Or not, I guess. I am on page 44 of the print version. It's chapter 3, section 3.3, the second to last paragraph. Does that help? Good. Oh, that's cool. It was like a quasi-quoter. Okay, so that's one of them. And it doesn't look the same. This one looks like, so yeah, this is what it looks like essentially. This version here, minus the get zip list. So anyway, and minus the I, but that's essentially what you would be doing. And subtract should be equivalent to just open parentheses and minus, although that might mean something different. It might be a unary negate. No, it looks like subtract. Yeah. Okay. So anyway, that's kind of interesting, I guess. I'm not sure we would ever use it because I'm actually perfectly okay with applicative syntax, but it was in the book, so I figured we'd talk about it. Okay. So in the realm of pure computation, it never makes sense to execute code if you do not want its return value, since that is only visible effect coming out of the call. For monadic or applicative computations, this is not the case, as you might want to execute one of these actions for its side effect alone, completely disregarding the value returned from the action. Haskell's standard library provides 3 special combinators for that case. A trick for remembering the names is that the argument that has no right angle next to it is the one discarded. Or left angle, I suppose. So we have the following functions. This one. That one. In this one. Alright, so let's highlight one at a time. So given an A, so this gives me a list of 1. Interesting. Oh, cool. So now we're on the same page, literally. That's fun. Okay, I've never used this before. Does it just throw away every value, or does it replace them with 1? Okay, so this is kind of interesting. So with, I imagine with, this is less weirdness, I suppose. But that's kind of cool. Okay. I don't think I've ever used this. So you just want to, I don't know when you would use, I could see this being useful, I suppose, but I'm not sure how exactly. Anyway, it's kind of interesting. So this one takes an FA, FB, so we can do kind of the same trick with that, but in the applicative context. Or you could even write hang on. You could even write just pure one and it would do the same thing. All right, and then the when the value is unit, like IO. Oh, okay. Is unit like IO. Can you give me a more concrete example? So if we had IO unit and you wanted to return an IO int, I'm not sure I fully get it. Chain IO operations. So you have like, you're saying you have like something like this. Huh? We can do this with, what does this do? Oh. But these don't actually change the order. Interesting. Okay. What was the other one? The other one is just to throw away the other piece. So we could do this. And that just throws away the first piece completely. Okay. That's interesting, I guess. I'm not using these functions yet, so I'm trying to come up with like examples of when you would use them, but personally I can't. But that's mostly because I don't have a ton of experience doing this. Okay, so we're coming back to our validate person thing. Oh, well, here's an example. Okay, so we're back to this function. I'm just gonna type it in here even though it's not. Okay, so let's say we had this function. We want this function, but we really only want, we want to validate the name and the age, but what we really want back is just the, I guess, the uppercase name. So you can replace this here. So you're still validating the name and the age, but you're really only returning the name, I guess. I don't have these functions in scope, so I can't really play with them. Okay, so we could do it this way. We could also do the following. Like this. This to me decreases, like this is not as, I don't like this very much. Oh, I have them implemented in one of the other chapters. I don't feel like doing it. I'm just trying to think about this. But essentially, you know, I think this is the most readable to me personally. This is harder for me to see, I guess. But yeah, you're basically just throwing this away and keeping the map to upper. So anyway, that's kind of interesting. All right, so until now, our only references to pure and point, which is the Scala version, by the way, of pure, were their close connection to monadic return and how they arise as the lifting of a nullary function that is a constant. This second behavior is rather useful when using applicative style to pass some functions free of side effects. Going forward to our person example, if we want to initialize the age to always be 20 years, we need to introduce an explicit anonymous function. Well, I don't have person. So let's just go create a person. I guess we do need this code now. No, that's to do. This is what I want to do. Great. Source here. Ordered a copy of Book of Monads after seeing the link of you stream a couple days ago, and it just arrived today. Oh, that's awesome! I'm so happy about that. That's great. You should tell Alejandro on Twitter that I'm making him money. It's clearly a joke, by the way. Please take that as a joke. Yeah, no, I think it's a fantastic book. It's really pretty, right? Like it's a very gorgeous book. I like it a lot. I really like textbooks, so like pretty textbooks are really important. I should just cat this. Yeah, I'm not. I would never ask for that. Would never ever ask for that. So we need validate person and all of this. Okay. Yeah, yeah, which is weird, right? You don't see. I like the holla holla get fmap. Oh, it doesn't read so nicely when you say fmap, unfortunately, but I like it. Yeah, it's a nice book. I definitely recommend it. It's especially good because it's a really nice introduction to monads and things. So I think this is what we need. It turns out apparently I didn't even implement these functions because we're really just using them to get types. All right, so we can go back to our REPL and continue. So we can write a function like this. right? And then we can get the type of f. Got it from the last Lambda conf. Oh, you got a scholarship? That's sweet. Yeah, that's definitely, it's a good thing to do with a scholarship. Buy the things you need. Or want. You don't need it, right? You can just want it. Okay. This is a function one can write, sure. We can also use the flip operator because why not? Flip person 20 name. So this would be like G of name. Fine. Yeah, so it says both solutions are far from perfect since we are polluting the description of the behavior with the explicit argument manipulation. Using pure point, we can find another solution, which involves moving the constant 20 from the world of pure values into the maybe universe. So you can also write h name equals person f mapped onto validate name applied to pure 20, right? And this reads from left to right a little easier. There's no nonsense here where you're like creating the partially applied person. You're just, doing the applicative as it was meant to be used, I suppose. How come it's only maybe a person? In case of nothing, just in case f isn't given a string. Oh, it's because of validate name. So let me pop that open real quick again. So in validate name and age, you might have a string or an integer that aren't valid. Well, it's mostly a string, I suppose. Well, yeah, I mean, you might be given the string 0 or something, and that's probably not a name that anyone's familiar with. So, like, maybe you go trying to read from the database to see if this is a real person, and then if you get nothing from either one of these, you end up getting nothing overall. So, okay, so it has to be given a string. It may not be a valid string. That's, yeah. So, and the same is true for integer. Like, what if you get a validate age with the value of 210, right? That doesn't make any sense. So, you need to have some sort of way to validate somebody's age as well. So if name and age are wrong, you get nothing overall. It's kind of the classic example of using applicative is in sort of form validation. So whenever you see applicative, actually, this whole this book that's what it's doing. It might make sense in the future. Well, I suppose that's true. It depends who you're talking about. Is a valid point. The context is important there, right? But that's what they're doing in this book, actually, going over. I haven't actually read it yet, but I think it's mostly about applicative and like form validation with applicative. But I wanted to support them because I think they do good work. Anyway. Have I mentioned that I like textbooks? 400-year-old shark. I didn't know they lived that long. A person shark? Could we validate its age? Okay. I like, oh, wait, well. I think, where did it go? Oh, here it is. Jeez, I'm blind. I think I like this a lot. I don't know that I've ever experienced this. What was his name? Would it be a valid name? Anyway, I like this quite a bit. I think it looks really nice. Okay. Anyway, that's how you could use Pure for just as an example. So I noticed there's a few more people who are watching as well. So if you have any questions, feel free to bother me. Tell me who you are. If you like Haskell, whatever you want. We're almost done with this chapter. So I think we've been doing pretty good with chapters as well. We've almost finished a single chapter per stream for this book, although it's probably going to get a lot harder very soon. And we've been doing about the same with Thinking with Types, so I'm pretty happy with our progress this far. Okay, so starting with version 8 of GHC, there's that language extension which I showed earlier, the applicative do, which repurposes do notation in section, well, it doesn't matter where the section is, to work with applicative combinators. The idea is quite simple, consider the following piece of code. So let's... Okay, so with applicative do, you can basically do things like well, I mean, just says action, which is kind of a weird way to put it. So actually, I want to see if I can write it with these constraints. Actually, that's kind of interesting. I didn't think about doing that. So we're gonna have an applicative f. Okay, well, it seems to accept the notation, but it just says use Fmap. So I want to try this real quick. But it seems to be working. Let's rename this just to example. The type signature says it enough. Okay, so just want to see if it compiles. So you can write example +1 pure 1. What's the what applicative context does it pick? I'm confused. Does it what's the what is it deciding F is? Sorry. Swarm Collective. Just listening while running updates on all the machines. I think I'm absorbing about 4% of what you say. Sorry. I wish it could be higher. I wish I could osmose into your brain. That's what I would hope for, but I don't think it works. I wish that I could do that with this content into my own brain as well. But you know, it is what it is. All right. So anyway, that's applicative do. So that's kind of cool. I'm still confused what context this is operating in. Like, what applicative does this choose? I mean, if you pick the container as list, that makes sense. But does it pick identity? I think if it was identity, it would literally say that. So, oh, time to take a drink. Matrix. What do you mean matrix? Oh, I get it. I see where you're going with that. Okay, so we're gonna code the matrix so that we can upload books into our brains. I like it. I like it. I'm into it. I don't know where I get identity. I mean, I would just have to make. I mean, I could make it, but there's probably a way to just get it. But it can't use identity, I guess, because anyway, I'm not sure. I'm not sure what it's deciding here. What applicative does this operate under? It just prints 2. It's not obvious to me. Anyway, okay. If anyone knows the answer to that, I would appreciate it. But I might ask, because I might ask in the another chat, because I'm confused. Okay, so definition using tuples. This looks like Scala code, so we might skip it. We'll see. Hang on. So we have approached the concept of applicative functor from the idea of lifting arbitrary pure functions. Since in Haskell functions are curried, that is, they take one argument at a time, a combinator like app does the perfect job, or does the job perfectly. In other languages like Scala, arguments are given in batches, making this combinator a bit less useful. What combinator should we use instead to lift these computations? Okay, so this isn't actually just Scala. We can write this in Haskell, but we'll do it in here. Illustration purposes in the REPL. Oh, actually, Newmaid said he wasn't going to be around because they're traveling, I think. I think that was mentioned, so, but I don't remember when. But I agree, we miss Newmaid when he's not around. Okay, so we're gonna write a function. Yeah. Triple nest, because it's a fun name, I guess. This isn't going to be a very fun function to write because it's quite easy, but so this is an exercise. I think it's intended for Scala people, but we'll write it. I mean, it's easy enough. They were here. They all left because NewMade wasn't here. He's more important than me at this point. Yeah. I agree. I agree. This is kind of a... In Haskell, this is an awkward function. Although, I wonder if we can do this in a more interesting way, but I don't think that we can. Which way is it? Yeah. It's kind of like, why am I writing all this? I don't even have to. Um, is this harder in Scala, maybe? Not really sure. Oh, I see. Okay, there's a function to do this. I see. So we can. I get it. I didn't see this before. So there's apparently a thing called a monoidal functor. I know what a monoid is. Oh, thank you. Did it seriously not rename that function? It can't figure this out? Gotta be kidding me. Do I have to do it here? Is that the trick? Or it just can't do function names, it can only do argument names. Very unfortunate. Okay, so we have a unit and I've not seen this type class before. Uh-oh. Haskell's pooping out. Okay. Note that monoidal also features a unit function, which can be seen as lifting a nullary tuple. Yep. The key is observing that a single f of unit may also be seen as a function unit to f unit, where the lifting is more explicit. Amazingly, applicative and monoidal functors define the same notation. We can see it by providing an implementation of applicative in terms of monoidal and vice versa. Interesting. Yeah, I think so. Yeah, more or less. So, okay. So, I'm gonna write these a little differently. Just so we don't don't break stuff we've already had. Oh, except let's restart the language server because it appears to be broken. So Fmap. Do I need this here? Or does this... Hang on. Let's go find this real quick. I don't know how to. Which one is it? Is it this? Okay. Should, I mean, do we? Let's not worry too much about this, I guess. I don't want to implement. Well, I guess I don't have to implement it, right? I can just write monoidal f. We don't provide an implementation of unit, but that doesn't really matter. Oh, yeah. And then that's just const. Throw away the other thing that it's given. Okay, cool. This makes sense to me, I think. So we give it f of unit, and then we just basically fmap a function that throws that unit away and plugs in something else. Okay. Let's write at prime. So we need monoidal f functor f f a b gx gy. Okay, let's change the shape of this to the other one that was there so that okay, so let's see what we got here. So this f is a function from a to b. We just tuple up is approximately well, it's not approximate, right? And x, which is an a. And then we just apply that function. Okay, that's fine. I think that's, yeah, this is okay with me. I'm not scared by this. Anyone having any issues with this? We're just taking basically the inner contents of these functors and putting them together and then writing a function that puts or adds them together, essentially. Or I'm sorry, applies the function to the value and then gives you back a functor of b. Anyone issues? Okay, and then we need to define the following. So we are going to define unit prime. So exercise 3.5. Find unit and okay, so unit is going to have the type f of this, and it's going to be applicative. Easy. And I assume we probably want to give this an easier name, but I mean, I think we can just put, like, we can just make it a funny looking shape that doesn't mean anything, like that. There you go. So, right, because FA is just this, we're basically just taking, I can just write this, oops. Just, this is really, maybe for your sake, you might be following along just fine, but I like to make sure. So this is, again, equivalent to FA, comma, right? Or, if you prefer, this. So it's a partially applied function with an A. Sorry. I almost have this right. It's, there we go. Right, so we have our functor and a partially applied tuple to a single A. So all we need to do is use the apply with FB to give us the complete functor we're looking for. Well, the result inside the functor that we're looking for. Does that make sense? I don't think that one's too scary. The function name is weird, obviously. This might mean other things. I was just trying to make something close to this. And this, by the way, just came from here, because star star is apparently already defined in Prelude. I don't know where it comes from, but we can look at its type real quick. Okay. I guess it's a exponentiation operator of some sort. So anyway, we'll use a different syntax just to make our lives easier. Okay. Apparently Scala has some sort of scream operator that does something. So its scream operator does the same thing as this, which just makes some code a little easier to write. It says, regardless of your language of choice, the facilities provided by applicatives to manipulate simple computations in context make them a great tool for writing monadic code. Even within do blocks or comprehensions, it's becoming increasingly popular to sprinkle some apply operators in order to obtain more concise code. Needless to say, applicative functors are a whole world of their own. What we've described here is circumscribed by their relationship to monads. Sure. Okay. So that's actually the end of the chapter, and technically the end of the stream, but if anyone has any questions, I would gladly answer them. Otherwise, I'm going to do my little plugs, and we'll call it a night. So, plug 1. You can get this book. It's actually quite a nice book, and I think Edwin's Roar would agree, and so would Oren. So, if you give if you agree, then just let me know. Oh, also, did you know you can support Haskell if you order things from Amazon? If you didn't know that, you can do that. You use smile.amazon instead. So you can get this book directly on Amazon, and I have a link here, so you can just write book, and you can get that. So Edwin's Words agrees. Nikito. Also, hi again. You've been here before. How's it going? It must be pretty cool to tell people who ask you what you do in your free time is say, I'm reading the Book of Monads. What was actually kind of a funny thing happened on the plane. I was flying a few weeks ago. If you remember, I was gone. I don't remember if you were here, but I was reading this book, and they're like, what is that? The Book of Mormon? And I thought that was kind of funny. Because it's kind of like an interesting book. It almost looks like it's leather bound, but it's not, right? So it's kind of an interesting thing that someone asked me. Yeah. So, but yeah, you can get this book, and we've had this conversation before, but the Kindle version does not look as nice as the paper version. So if you really want the nice looking version, you should really spit up the extra $4 and get the paperback version. You won't be disappointed. The code for this is always available online, so I have you can just go get it, and we'll actually we'll commit this code right now. Hang on, I need my keys. Give me 2 seconds. Oh, they're right here. There we go. I can type, I swear.